So what I'd like to do is basically consider that and have a discussion about Gauss divergence theorem and the class of surfaces for which the Gauss divergence theorem is true actually. Obviously you can extend this class more and more and more. Okay. So far what we have, so by parametric surface you mean that you have a two-dimensional region, okay, and to a two-dimensional region, for example, in UV plane, you have a map, okay, that you can call it to be the parametrization, and that parametrization throws all of this, points into, for example, in R3, and you get, what is called a surface here actually. So if this is U, should be an open set, okay, and this is really P of U in 3 dimension, and then to each corresponding point here you have a corresponding point here, because if you map all of these points in 3 dimension you're going to get P of U, and you call this as a surface, and then we have some conditions on P that it must be smooth and all of the things. But the basic assumption is that like this should be really a one piece actually. If you want to see it as a for example, intuitively, physically, so I have a two-dimensional piece and I'm mapping it through P onto a 3-dimensional piece. So this is just one piece, while in reality the surfaces are not just one piece actually. So there are a number of pieces to put together. So number of surfaces put together makes a surface actually. For example, have a look at for example, surface of this book actually. Okay, so I can say that this surface does not fit on definition of this surface actually, because what does this surface need is that so this allows you to just define one piece actually. So you can treat this part as a surface individually, like this is a surface, this is a surface, but does this definition accommodates that the entire surface area of this given surface is really a surface? Okay, so what you need to do, you need to extend your definition. So what are the key things that you see in this surface? So you have a number of surfaces, okay, like 5, 6 surfaces, they are joined together, okay, and wherever they are being joined, you have, what do you call these, these curves actually, okay, so the number of curves. So that's when I'm joining this surface with this surface, so they are being joined at a curve actually, okay, and you will see that obviously if you want to have a similar kind of a P here, you will have a problem here, because these are the non-smoothness points actually, because here you have the sharp changes, so these are like the kinks actually. Are you getting the point? Okay. So if you want to define this as a surface, I'm going to call it's a piecewise surface, not a surface as a whole actually. So there are lots of pieces, 6 pieces put together create a surface, and wherever these pieces are meeting with each other, okay, so you have these curves, okay, are you getting the point? And I mean, if you, for example, get rid of these curves or you ignore these curves, then I can treat this surface as a single piece actually, okay, and I can say that I have a P, okay, that gives me this part, this part, this part, and this part, and every other part, and it's smooth, but it's not smooth on, what do you call, boundaries actually. Okay, so that's just one kind of a surface. For example, you take, so just, take the surface of a mouse actually. Think about that's another surface actually. So the bottom is a surface, so ignore this, rest of the things. So the bottom is a surface. Even if you include the rest of things, it would be still possible to define it. So bottom is a surface, and the top consists of 3 surfaces again actually. So 1 surface, 2, 3, and what do you call 4. But whenever these 4 surfaces are put together to create a new surface, you see that when you are joining them, you are getting these curves actually as a result actually. Are you getting the point? So what we can have So what you can essentially do is that I can treat this entire surface as a parametric surface, but a piecewise parametric surface, okay? Because for each of the piece you have a parameterizations, and you can combine all these parameterization to get a parameterization of the entire, what do you call, surface. But those parameterizations are not defined on these, what do you call, curves, the controversial point where, you know, the surfaces, you know, the surfaces are changing radically, okay? So you don't have smoothness here actually. Are you getting the point? So I would like to define piecewise parametric surface, okay? So let me put a precise definition. So I'll not give you the intuition, because I hope that I try to give you some intuition actually. So what do I mean by piecewise parametric surface? So I'm going to say I have a subset of R3, okay? So the mouse is a subset of R3. Its surface is a surface of R3. But it's kind of a surface of R3, and I'm going to call this surface, you know, a parametric surface. But it's not just a because if I just call it a parametric surface, I just mean this actually. But I know that is not just one single piece. But there are multiple pieces put together, it gives a. So it's a special kind of a parametric surface, parametric piecewise surface actually. Okay? So parametric, yeah, piecewise parametric surface. You can also write it in this manner. That you have piecewise, okay, piecewise parametric surface. So we're going to call a surface a piecewise parametric surface, okay, if following is true. If you can have an E that is a part of the surface, and this E is really the collection of all, you know, collection of all these curves where you don't have smoothness actually. So the collection of all curves which are made by gluing two pieces of the surfaces actually. Okay? Are you getting the point? Yes. For example, in this book example, how many are going to be the curves? So are there going to be 1, 2, 3, 4? 6. Okay? No, not 8. 8. So there are going to be 8 curves actually. So if you put each of these curves and union them, okay, so the E is such kind of a set actually. So the E is what? If we can find there exists in E that subset of the such that E is a union of points, okay. Actually, you can also have a surface which are, for example, non-smooth only at some points. In other words, surfaces are joined together but only through some points actually, not the curves. Okay, so it could be E could be the union of points or curves actually. Okay, curve segments. Okay. So if E denotes, so you should have an E, the subset of S that is the union of points and curve segments. And what is the role of this E? The role of this E is that if you look at the surface, ignoring E, then this S less E is a parametric surface actually. Is a parametric surface. Are you getting the point? So it's a parametric surface. So except, you know, if from S, if you take away this E, then its rest is, you can treat rest as a single piece actually. So what essentially you are saying, so this is a clever way to say that, okay, you have different surfaces, parametric, you put them together, you glue them together, so you're going to get a new surface. Okay, and that new surface can be treated as a single surface, but in that definition of, you know, but there would be an issue, you know, to call it a parametric surface, that because there can be some segments or curves where, you know, you don't have smoothness actually. Okay, so what you are saying that if you ignore those, okay, all curves and points where the function is not smooth, then you can treat it as a single piece actually.
So, लेकिन फिर ये मसला हो सकता है ना कि वो complete parameterization नहीं होगी ना उस सारे
Yes, so what will happen is that if you have multiple pieces, so you will have a trick to define this, what do you call parametric surface. In other words, that imagine there are two surfaces. For example, you think of a cylinder actually. Okay? So you have this cylindrical part and you have a lid and a bottom actually. Okay? So in that case, in case of the cylinder, what would be the E? So the E is going to be the top circle and the bottom circle actually. Okay? Because you need to kind of weld them, you need to glue them to make this, what do you call, a cylinder actually. Okay, so what was your question?
Sir, कि वो complete parameterization नहीं
Okay, so the point is, what is the parameterization of cylinder including base and the lid? So I'm going to take the parameterization of lid and the parameterization of what do you call bottom and the parameterization of what do you call cylinder, and I'll define a parameterization for entire surface. Okay, that is going to put together, but and this is easy. So what you can do roughly is that I can define P as a parameterization, in such a way that this parameterization is equal to the parameterization of P1, where the P1 is the parameterization of, for example, bottom, and it's equal to, for example, P2, where the P2 is the parameterization of cylinder, and P is equal to P3 if you, okay, so maybe I write it precisely. So if I say that I want to evaluate P of UV, so you need to see UV lies where actually. Does it lies on the bottom, cylinder, or a lid? So if it lies on the bottom, I'm going to use the output of PUV as same as P1 of UV, where the P1 is the parameterization of bottom. So you are reeling, extending, and creating a new parameterization. But obviously this parameterization is not going to be defined on the boundaries. Okay, the boundaries of the bottom and lid, in other words, the circle of bottom and lid actually. Yes, you can get
even for cylinder, complete parameterization doesn't exist because there is a contradiction between 0 and 2 pi. We only include either 0.
Yeah. So you have to do everything in such a way that your definition meets with your standard definition, obviously. Okay, but what I'm saying is that yes, you can create a single parameterization, okay, that can cover really the entire surface actually. Okay, that's what is really the key point. Okay. So now is it visible? Is this visible?
नहीं हुआ
नहीं हो रहा. Light on कर दें. है कोई light?
लाइट ऑन हो जाएगी लेकिन सर अल्फाज समझ में नहीं आएगा सर, ऐसे हो रहा है.
अच्छा.
यस सर.
ये तो move भी नहीं कर रहा. So shall I get rid of this again?
Yes, sir.
Okay. It's going to take a lot of time. ये move तो करता तो था पहले. हाँ करता है. थोड़ी सी मेहनत करनी पड़ेगी. अब ठीक है. अब मेरे ख्याल से दोनों आ जाएंगे इधर. वो भी रखा हूँ अंदर रहेंगे. चलेंगे. Is it working? Yes, it's working.
सही है, सही है.
All right. Now, if you remember, if you have a parameterization P, and so I mean, if you remember, so I will be very much interested in one particular kind of curves. If you remember, if you have a smooth map, okay, if you have a smooth map, say from some open set into R, in other words, where the U is some open subset of R2, okay, so if you have a smooth map, then through this smooth map, I can construct a surface. And how can I construct a surface? Just consider the graph of it actually, uv and f of uv. Remember?
Yes, sir.
So I can call it P of uv, okay, and I know that this would be a, what do you call, the graph surface or the Monk patch. Okay, you can call it a graph surface or the Monk patch. Okay? So if you have a scalar field, okay, define in an open domain, so you can, its graph can be treated as a surface. But the crucial condition that you need here, that f must be smooth actually. It must be smooth. Question. Can we relax this condition? We need to relax this condition actually. So imagine I have an f and I want to look at the graph of those functions which are smooth in some sense, but not on entire region, but on some part of, for example, u, they are smooth. Not on entire u, but on some part of. So it's like making it a relaxer. By the way, another thing that I should, piecewise parametric surface is a generalization of parametric surface. Think about it. Okay, it's a generalization of parametric surface. Why? Because it's like the same. Piecewise continuous function is generalization of continuous function because the continuous function is one piece.
Yes, sir.
So parametric surface is just one piece of surface, but you can have multiple pieces of surface. So it's really so you are relaxing the conditions. You are talking about a wider class of the surfaces actually. Similarly, if you relax the assumption, here you need the assumption that f must be smooth on the entire u. But I'm saying that let's not assume that it's smooth on entire u, but on some part of u, it's smooth actually. Okay. The question is, can we have graph of such kind of functions which are not smooth on the entire domain but on some part of it? And if we can have such function, can their graph be a surface? Okay, and that would be an interesting question actually. And the answer is, if you think cleverly, you can have graph surfaces actually. So let me give you a definition. So let me tell you that what kind of function I'm talking about when I'm saying that I don't have a smooth function. So imagine I have a function f. Okay. So in other words, not only I extended my class of surfaces and made it bigger, so I would like to also extend the class of f and make it a bit more, what do you call, bigger. Okay, so that such kind of things can be accommodated actually. Okay? Okay. So suppose you have a two-dimensional region. Omega is sigma is a two-dimensional region. So it's in subset of R2. And I have a map f from this sigma into R. Okay, so I have this map sigma into R. So I'm going to say that such an f, which is defined on some chunk of R2 into R, is piecewise smooth. Okay, is piecewise smooth if what happens? Number one. So the number one is piecewise smooth if there exists an open subset. In other words, there is a part of sigma. Okay, there is a part of sigma where f is smooth. So if we can find an open subset u of sigma such that if I restrict this given f, which was defined on entire sigma, onto u, then it would be a map from u into R is smooth actually. So f is not smooth on entire sigma, but is smooth on some part of the sigma. Okay? And the second thing is that if you look at the sigma, okay, by removing this part where the f is smooth, then this part of sigma other than u is either some finite number of points or some curves actually. Union of finite number of points or curve segments. So what do I mean by that? What do I mean by that? Imagine I have a region that is, for example, triangular. So I talked last time also about it. Okay, and this is my sigma, and I have an f that is defined on this triangular region. Now, these kinks are going to be trouble-making points. Are you getting the point? Kinks are going to be trouble-making points. So, in other words, you can't have smoothness here actually. The question is, what should I do in such a way that, so what u should I choose, okay, that is open, okay, and in other words, so f is defined here, so what should I do so that I can, I can come in agreement with this definition actually, okay. So here's the thing, so these kinks are the points, and you need an open set. So what is going to be the open set within that actually?
Open ball.
So what you can do, either you can take a ball actually, for example, or you can say that, okay, just get rid of these, boundaries actually. Now that's an open set. Okay. So now I can say that, okay, f that is defined on this is not smooth because it's not smooth on these kinks, but on this region it's certainly smooth actually. So this is your u. Are you getting the point? And what would be sigma minus u actually? So it's going to be only these, what do you call, lines actually. Are you getting the point? Okay? So this really extends the previous smoothness. You don't want smoothness. So what are the difference between the previous definition and this definition? The previous definition is a particular case of, for example, this definition. Okay? In other words, if you take omega to be entirely open, okay, then a piecewise smooth function is smooth function. Are you getting the point? So this can be a particular case of this definition. Are you getting the point? Okay. And why this would be useful? In a moment I'm going to write a, for example, concrete example of it, and you will see that this is going to, what do you call, what? So here's an example of it, a more concrete example. So consider a function f of x, y, and you define it to be the absolute of x. Okay? Where you are choosing your x and y, for example, from a rectangle. Minus 1 cross 1 into minus 1 cross 1. Okay? How does the graph of this is going to look like? If I say that this is my x-axis, y-axis and z-axis, how does the graph of this is going to look like?
V surface.
So it's going to be a V kind of a shape actually. Okay. So it's not only going to be V, but it's actually going to be, because think about it, to each Y you have a V.
3-dimensional V.
Okay, so it's going to be a 3-dimensional. So it's going to be this, like something like this.
V surface.
Okay, so it's not going to have a width actually. So it's going to be that you have two really, or maybe more better would be that if I just take 2 pages actually. Okay, it's going to be something like that. Are you getting the point? Okay. Now, in this example, so let me just get rid of it and try to show it that it's going to be something like this. Okay, you may going to be something like this, okay? And what is the role of the sigma here? So the sigma is what? Sigma is this region,
Rectangle.
this entire rectangle. This entire rectangle. Are you getting the point? Now on this entire rectangle, f is not certainly smooth. Why? Because you have these bunch of points, okay, where the function is not going to be differentiable. It's not going to be differentiable actually. So in other words, which are going to be the points where you don't have differentiability? So all those points where x is 0.
Regularity.
Okay, so you're not going to have differentiability. And you remember, what do we mean by a smooth function for us? C1 class functions. So in other words, continuously differentiable. So that's what we call, so which are continuous and differentiable as well. So that's what my definition of smoothness is at the moment. So what should I do? So the sigma is where? So the sigma is really the bottom of it actually. So a rectangle in dimension actually. So that's your sigma. Okay. So in sigma you have a strip actually where like x equal to 0, where you don't have smoothness actually. So what should be my u now? What should be my u now?
So we take x.
So take everything. So you can take -1 to 0.
Yes.
Okay. And cross union
Yes.
0 to 1. So let me.
सही है.
यही होगा. Okay. So if you choose, for example,